Okay, for hydrogen lines, we have a shortcut, right? If we're going from level 6 to level 3, which is our first transition, then we know that 1 over that wavelength is equal to the Rydberg constant times the difference in ends. We take the larger, if you do the smaller minus the larger n, like this, then you get 9.14 times 10 to the 5th. And so the wavelength, which is the inverse of this, is 1,094 nanometers. Okay, so that's the wavelength of the photon that goes from 6 to 3. That's transition A. Transition B is from 3 to 2. Okay, so a similar calculation. Do 1 over 4 minus 1 over 9 gives us 1.52 times 10 to the 6th. And so lambda is 656 nanometers. And then third transition from 2 to 1 gives us 8.23 times 10 to the 6th, which is a wavelength of 122 nanometers. Okay, now this wavelength is called Lyman alpha. It's the first wavelength in the Lyman series that goes from 2 to 1, 3 to 1, 4 to 1, 5 to 1, 6 to 1. This wavelength is Balmer alpha, which is the series 3 to 2, 4 to 2, 5 to 2, 6 to 2, and so on. Now in part B, they're saying they're going to take this transition here, this Balmer alpha transition, and they want to know how many hydrogen atoms will need to be emitting to get total 15 joules of energy, right? So we're going to use the equation that the total energy is equal to the number of photons times the energy per photon. Now the energy per photon in this case is just, I guess we would take the, let's see, if you're emitting from 3 to 2, then the amount of energy releasing is negative 13.6 over 4 squared minus negative 13.6 over 3 squared. Wait, no, over 2 squared. Oh, I'm an idiot. Sorry. It's 13.6 over 3 squared minus 13.6 over 2 squared. That's the difference in levels, right? So let me just quickly draw a little energy level diagram out here. So we got n equals 1, n equals 2, and n equals 3. Okay, so if we're going from 3 down to 2, then we're releasing an energy equal to that energy level difference. To find that energy, we subtract, right? We take this energy here minus this energy, and that energy is what's released. Right, but remember that this energy down here is more negative, so that's going to end up being a positive number. This is in units of eV. So if you get minus 13.6 over 9 plus 13.6 over 4, you get 1.89 eV. Okay, now I'm going to need to convert this into MKS units, so 1.89 eV, I'm going to multiply by the number of joules per eV to get 3.02 times 10 to the minus 19. Okay, now I'm going to return to this. I know that 15 joules is equal to the number of photons times the energy per photon, which is 302 times 10 to the minus 19. So if I solve for n, I get 5.0 times 10 to the 19th. That's how many hydrogen atoms are needed to get 15 joules of energy. This is how astronomers figure out how much hydrogen is in interstellar clouds and in stars and so forth. Is you calculate how much energy is being released from a cloud by looking at the total strength of an absorption or emission line, and then you just divide by the energy in that line, and you can get that.